See, you haven't been here, but you already know how to hit record. It's interesting. Okay. It's all very confusing for me. All right, I will begin with a word of prayer. Dear Father, we thank you for this day. Again, Lord, I thank you for these students. I pray you to help us use this time wisely, just to gather together our thoughts about how to take partial derivatives and also how to understand them, Lord. You know, I pray. Amen. All right, let me get started here. And so there is no, there's no condemnation here in terms of if you can't do it yet. I haven't even recommended homework, because I just thought it would be a good experience for you to try to do it. And if it didn't go well, it didn't go well. No big deal, right? So let's see here. Let's assess the damages. Partial F, partial F. Now, this to quote my community college professor, this dog will not hunt. This F is no, not supposed to be there. We have partial x acting on this expression. That altogether would be partial. What would be fx, f sub x? All right, which is just another notation for partial f, partial x. I mean, in other words, this is partial f, partial x, and this marker is worthless. But anyway. Yeah, not quite. So, yes, partial f, partial x, and a. All right. Now, is that derivative right? Yes, because the derivative of y cubed with respect to x is 0, so we're good. Again, same syntactical problem here. That's not partial f, partial y times that. It's partial y of this. This is an operator. It acts on this expression, and it gives me this partial differentiates to x. The y is gone. Y differentiates to 1. Y cubed differentiates to y squared, so we get 3y squared. So indeed, I agree. This would be, we could use f sub y, or we could use partial f, partial y. It's good. Now, down here, fxx, fxy, fyy, these are notations for second partial derivatives. So fxx equal to 0 is right. So fxx is what? fxx is actually partial x of, partial f, partial x is another way to look at it. But this is exactly y from the previous problem. So partial y, partial x is 0. That's why that's 0. Fxy is 1. So something kind of funny, right? If you calculate partial y of partial f, partial x, what would that be? Partial y, partial f, partial x here would be y, right? But what else could you do? You could also look at it as, you could calculate this as well. Partial x of partial f, partial y, what would that be? Partial x of what? Let's see, your partial f, this was partial f, partial y, right? What's this differentiate to? That's also 1, yeah. So this is an example of a theorem for most decent functions. We have this, that fxy is equal to fyx. In other words, if you have partial derivatives with respect to x, then y, or versus y, then x, we'll get the same outcome. Now, technically speaking, this fxy, what that means is the y partial derivative of fx. That's the way the notation works. So if I rewrite that in terms of the partial notation, that's actually partial y of fx. So it's kind of weird, but this is actually partial squared f, partial yx if you unwrap it. But I just got done telling you that for most decent functions, this is actually the same mathematically as that. This is Fubini's theorem. So your inability to remember which notation comes first doesn't really hurt you. But anyway, that is technically what this means. This is the y partial derivative of fx. All right, let me erase that so it's not so much clutter here. Excuse me. Fyy is 6y. Does that make sense to you guys? The second partial derivative with respect to y. Second partial derivative with respect to y just differentiates this with respect to y. The x goes to 0. 3y squared differentiates to 6y. Are we all in agreement? I hope. Problem 2 tilde. Yeah. So partial g partial x is partial x of this expression. Y is constant, so that differentiates to 0. Sine differentiates to cosine, but the chain rule says I still have to multiply by the partial derivative with respect to x, the inside function, which is xy. So that gives me y cosine xy. And then partial g partial y, similar but different. This time y squared is not constant with respect to the differentiation. So we pick up a 2y from that. We get cosine of xy times the derivative of the inside function, which this time produces an x, right? Because the point here is partial y of xy is equal to, I mean, you could write a product rule if you wanted. This would be partial x partial y plus x partial y, right? This is 0, and that is just x. So that's why this right here simplifies to just x. All right? Or you could just think of it, x is constant. I pull it out, and I have x times partial y, which is just x times 1. The second partial derivatives, well, let me see here. Partial squared g partial x squared. So that would be partial x of y cosine xy. Agreed. I think the first term is right. So the first term is what? It's y times the partial, I mean, this right here, what's this coming from? This is y times the partial derivative with respect to x of the cosine of xy, right? So that makes sense. We can pull the y out. We differentiate the cosine xy with respect to x. That gets me a minus sine xy times the partial derivative of the inside function. The partial derivative of xy with respect to x is just y again, which is why I get minus y squared sine xy. That's true. And then what's this term over here? Well, I think she was thinking about the product rule, right? Because we've got y times that. It's a product of functions. But the thing is, it's an x differentiation, right? So really, this one is partial y partial x. There's a partial y partial x here in the differentiation that you knew something was wrong. I know that. So this is 0. This term is not present is the point. So in short, the answer is just minus y squared sine of xy like that. So let me redo that slowly and carefully just for a second here. So in other words, partial squared g partial x squared partial x of what was partial g partial x was y cosine of xy, right? So here's the way I think about this. I just think y is a constant with respect to the x derivative. So I pull this out front. See, this is y partial x of cosine of xy. That's the way to think about this. And then this differentiates to minus sine of xy, right? And then chain rule says partial x of the inside function, which this time is xy. Now that partial derivative with respect to xy, this just simplifies to y. So that's why I get minus y squared sine of xy for the answer here. Does that make sense? I hope it makes sense. Okay, I'm going to move on then. The other derivative would be similarly calculated. Here we're asked to find the gradient of this function, f of xy, x squared plus e to the xy. So that means we have to put partial x, and partial y in a vector. Very good. And again, so this is a very popular wrong notation with you guys. So this does not mean we multiply that times that. The partial x is not an operator. What is an operator? What acts on functions, acts on expressions? Partial x. That is an operator. It can act on this logically. This would be multiplication of a function times something, which is not what we mean here. We mean that partial y acts on this. And if I'm going to, it's a partial. It's partial. Let's see here. So partial x, so that's a 2x. Very good. This differentiates to e to the xy. Now, why is this y here? Chain rule, right? What's the partial derivative of xy with respect to x? Right. So that's why that y is here by the chain rule. Now, the partial y, the x squared 0, and the e to the xy differentiates to x e to the xy. Very good. So, you know, again, I'm just quibbling over notation, but that kind of matters not to write that, okay? Partial x, an operator at x on things. I mean, I could say that this, oops, it is true that altogether this is equal to partial f partial x, right? Or you could write f sub x if you wanted. And this is partial f partial y, which we could also write as f sub y if we wanted. You know? You're like, 2 notations is not enough. Please, this would be so much better if you could give me yet another notation for the same thing. Since you've asked, sure. So this is also sometimes, and I like this notation like that. So sometimes we'll use just a partial x f. This abbreviated partial notation is sometimes very handy. It gets across the idea and doesn't suffer from some of the kind of annoying aspects of the f sub x notation.
So that x is a subscript still, though?
Subscript, yeah. F subscript. Partial subscript x is a partial derivative with respect to x, yeah. Popular notation. It's a good notation. So in that notation, while we're at it, in that notation, this would be partial x, partial y f, whereas this would be partial y, partial x f. You'll sometimes even see people write stuff like this, partial squared x y f. There's all kinds of variations on this kind of notation that is at various points helpful. All right. I mean, calculus is a language. You know, yes, we're trying to learn skills, but we're also trying to learn how to communicate with other people. So that's why I introduce other notations. All right, here. So what do you guys think? Is this legit? I think we have, the first one's, I think we're good. Because the variable's the base. The exponent is like a fixed thing, right? So it's like x to the n differentiated with respect to x. It's a power function, so it gets the power rule. Good. Next, the variable is in the exponent, so this is an exponential function. We should differentiate it like an exponential function. So I got a 2 log x, x to the 2y. Do you guys, I'm gonna agree with that. I'm gonna add some work. So this is the natural log of x times x to the 2y partial y of 2y, right? And that's why he writes, or she, I forgot, my apologies, 2 natural log of x, x to the 2y is the answer, and that's good. Yeah. Chain rule is where that 2 comes from. Very good. Hey. This is on all of you. Because every last one of you knew that you were.
Yeah.
Somebody did say it? All right.
Yeah,
You didn't press the issue either, did you? Interesting.
well, I wasn't gonna oppose it, I was just saying.
Yeah. All right.
They saw what happened when they spoke up that someone wasn't assigned the calculus.
Yeah. I'll do it for you guys. So this is 1 over the square root of xy. So that, let's see here, let's rewrite that like this. This is partial x of xy to the what? To the minus 1/2, right? And so by the chain rule, that is minus 1/2 xy to the minus 3/2 partial x of xy, which is minus 1/2 xy to the minus 3/2, and this differentiates to y. And so, lo and behold, we've got ourselves a minus y over 2 times the square root of xy cubed, if you like. Or, of course, you could just as well write it minus y over 2 times xy to the minus 3 halves. I don't really care. Whichever floats your boat. They each have their place. By symmetry, can you tell me? By symmetry, what's partial y? What's that? Yeah, negative x over 2 times the square root of xy cubed. Yep. So we just interchange the role of x and y. The calculation is otherwise the same. Right? All right, problem 7.
For that one,
Yep.
wouldn't you write the answer in the vector notation?
Oh, I'm sorry, I forgot my question. Thank you, yes. So, in fact, this, gradient of f, so looking at that, I can make my life easier by just saying it's really, what, minus 1 over 2 square root of xy cubed, right? And then I'll just keep in my, my x and my other way around, right? Yeah, sorry. My y and my x. So I can factor out that scalar function from the gradient. Make my life easier. Thanks for asking me. I forgot my instructions. All right. So one of the things I promised I'd prove for you today, I guess it was a slight lie. I made you prove it for me, which was that partial x is 1. How do we prove that? So the way to prove partial x is 1 is we need to look at the function, which is x, the x function, right? So what's the x function? I take in xy, I spit back out x. This is the x function, right? So to calculate the partial derivative of big F, so defined, should tell me what the partial derivative is of x with respect to x. So I'm going to calculate partial x at the point x naught, y naught. In other words, partial x at the point x naught, y naught. By definition that we gave yesterday, that's the limit as h goes to 0 of this minus that, divided by h. You see, you notice the x naught, I added h there, but I fixed y, right? Y is fixed, and the x naught we add h to. This is the definition. Now, when you actually put that into practice, for this function, that's x, hey, not x naught plus h minus x naught, right? The x naughts cancel. Yes, we could use L'Hopital's rule here, but we could also, math majors know too much. Let's see here. 1 is that algebra simplifies to 1, which is 1. But, I mean, yes, but this is a very unnecessary use of L'Hopital's rule. Anyway, yeah. Okay, guys, so how would you, for example, while we got this on the board, what if we wanted to calculate partial x, partial y? Suppose I erase that x and change it to a y. What would this change? So instead of fixing y, right, we do y naught plus h. That's the definition of partial x, partial f, partial y. We do y naught plus h, like that, right? And so this, when you look at the function at that, it doesn't have plus h anymore. It's just got x naught. And so instead of having h over h, you get 0 over h. And 0. So partial x, partial y is 0. Not especially exciting, but you can prove that partial x is 1, partial x, partial y is 0, partial x is 0, partial y is 1, from the definition with simple arguments like this. I often put this question on the test. All right. To show from the definition that partial x is 1, or partial x, partial y is 0. I put that on many of this particular test in Calculus 3. That's a very common question on my tests. All right, so here we go. Oh. Whoa. True. Interesting. All right, I'm afraid I'm going to get fished in. I'm just going to have to recreate this one from scratch. So this one, what I would do is I would say, okay, well, that is the natural log of 3, right, times 3 to the x squared minus y squared. And then I partial differentiate with respect to the inside function, like so. And so that is just, you know, natural log of 3 times 2x times 3 to the x squared minus y squared. Now, we might agree. So the answer here is missing a very yeah, so the thing that's missing here is you forgot to multiply by the derivative of the inside function, right? That says I have to multiply by 2x here as well. Then up to an interpretation. I mean, that's what I have there. Now down here, partial y, 3x squared. And so again, minus 2y, and then you'll have the right answer. You got to differentiate by the inside. The inside function is minus y squared, right? So partial y of that. Now, I like that you split off the 3 to the x squared using algebra and just treated it like a constant. That's great. You know, it's good work. Problem 9, partial x of this. So we've got e to the x squared times e to the z. E to the z is constant. So this arrow bothers me. You mean equals, right? So e to the z looks like a 2 to me. I can't tell. But so that criticism of my writing as well. But anyway, e to the z pulls out. Very good. Parentheses here wouldn't hurt. Let's see here. And then you've got partial x of this, which you've got for me a 2xy e to the x squared y times e to the z. I think that's right. Of course, the other way we could do this, just, you know, here's another way to approach this. This is e to the x squared y plus z times the chain rule, partial x of x squared y plus z, right? Which is this differentiates to 2xy, as you pointed out down here. Very good. E to the x squared y plus z. So you could do it this way also. That's I mean, what you did was not wrong, just different ways of looking at the same thing. Let's see here. So here we're calculating partial f, partial x, and partial f, partial y for this guy. And something neat happens, right? So you get 1 over 2 times the square root from the outside function, then multiply by 2x, because that's the derivative of x squared plus y squared, right? So the 2's cancel, and we end up with x over the square root of x squared plus y squared, and by symmetry, y over the square root of x squared plus y squared. So if you really look at it, what we've shown is that partial r, partial x, is equal to x over r, and partial r, partial y, is equal to y over r, where r is the square root of x squared plus y squared. Of course, that is the polar radius. So this is kind of a nice result for us to kind of stick away for later. The partial derivative of the polar radius with respect to x is x over the radius. The partial derivative of the polar radius with respect to y is y over the radius. These are kind of neat derivatives to know about. All right. Well, I hope that the mechanics of partial differentiation is starting to get boring. Well, anyway, at least if I were to ask the same set of quiz questions tomorrow, it wouldn't be stressful, right? Well, it should be stressful because tomorrow's Saturday. And if I'm asking you to come in and do a daily quiz on Saturday, it should bother you more. It would bother me if you asked me to be here tomorrow. I mean, I'm not sure what I'll be doing, but probably not calculus 2. All right. Yes. Attendance. Thank you.
That deserves some points right there.
Yeah, I think actually, given the timing, that might be actually worth something. So Joshua has been waiting to score some sweet attendance reminding points. Well played, Joshua. Just the right kind of time to remind me. You played the game well. This is a game you guys can play. I mean, this is my forgetfulness is an endless source of points, really. And now I got to find your name, though. Maybe I'll just give him. I found Nathaniel's. Maybe I'll just give it to Nathaniel. See here. There's other Joshua. Oh, it's in here somewhere. Ah, there we are. All right. Well, that took entirely too long. I'm sorry, guys. I seem to have eaten up an inordinate amount of class time with teaching you the mechanics of partial differentiation, which is unfortunate, because we really should be talking about the interpretation of partial derivatives as it relates to the directional derivative. So let me get on to that. I mean, it's fine. We're not behind or anything like that. It's just, you know how I am. All right. So, theorem, definition in some books, the directional derivative in the u-hat direction of f at the point P, it's given by the gradient of f at the point P dot with u-hat. Now this formula right here, this works just as well in 2 dimensions as it does 3. Let me unwrap it again in 2 dimensions. For n equals to 2, if we have u-hat is ab, and if we have the point P as x naught y naught, then this specifically becomes du hat f at the point P is equal to partial f partial x at the point P times times a plus b times partial f partial y at the point P. Right? Now, guys, what did we learn about dot products? Like, let's think about this. So this describes the rate of change of the function at the point P in any direction u hat. Right? So, specific example. Suppose we had f of x comma y equal to x squared plus y cubed, just to keep it relatively simple. And let's study the point P equal to, I don't know, how about 3 comma 2. So here's my question. What is min or maximum rate of change for f at that point? What direction does it happen in? So I've changed it up a little bit. I mean, last class I was saying, here's a given direction, calculate the rate of change, right? We define that. Now I'm kind of opening up a new can of worms. I'm saying, what if we think of AB being variable? What AB makes the rate of change the largest? Let me just kind of put it out there. Right here, this is a dot product, right? So what is this? This is the magnitude of the gradient, right? At the point P times the length of u hat. What's the length of u hat? 1. And then the cosine of the angle between them, right? Where I'm saying that this is the gradient of f at P, right? And this is your u hat, and theta is the angle between them, right? Now that I write that formula, can you tell me what u hat should we pick to make the make the rate of change as big as possible? We want to make the direction line up with what?
The x-axis.
The x-axis, the y-axis. You guys are still answering about this specific one, aren't you? I'm saying up there. You want to make u hat line up with what? Not x hat. No. The change in FP, right, the gradient. You want the u hat to be in the direction of the gradient. The gradient points in the direction of maximum change for the function at the point. That's its meaning. If you want to decrease as fast as possible, point the opposite direction to the gradient. Right? So the gradient tells you basically which direction you want to go to level up as fast as possible. So here, for this specific one, all I got to do is calculate the gradient, which is easier, right? At a generic point, it's what? 2x, 3y squared, right? So evaluating at the point in question, which was what? 3, 2, what do we get? I got to plug in x equals to 3 and y equals to 2 in this 6. So I get 6 and 12. Very good. So that's the gradient at p. What's the magnitude? What's the magnitude of the gradient at the point 3, 2? It's the square root, right, of 6 squared plus 12 squared. So that's square root of 36 plus 144, whatever that is. Square root of 180. It's about 13.5-ish, right? Give or take. 13 squared is 169, 14 squared is 196, I think. So it's between that. So if I ask you, so I'm at the point 3, 2. I want to go in the direction in which the function changes at the rate of 15. What direction do you tell me? You should tell me to go fly a kite or whatever your favorite, colloquialism is. Tell me to go watch American Idol. I mean, whatever you find most offensive. Whatever. I thought that was gone. I thought we were safe. And why are people saying they're happy about this? I don't understand. I thought we were past that. It seems like it's multiplying. Now we've got this 4 show. We've got the American Idol coming back. And there's still that other thing with the people. The voice. Yeah, the voice. Can't Carson Daly just be content with his middle of the night show? Just leave it at that? I mean, like, he's got that show between 2 and 3 or whatever. I'm sorry, I digress. So the point is, no, if you wanted a direction which this function is changing at rate 15 at the point 3, 2, you cannot accomplish that. The maximum rate of change of the function at the point 3, 2 is about, it's the square root of 180. Right? What if you wanted to go in a direction which makes the rate of the change of the function at 3, 2, 0? What if you want d u hat f 3, 2 equal to 0? For u hat equals to what? You tell me. Answer this. Question. Fill in the blank. How do you make the dot product 0? Negative perpendicular, right? So our gradient, right, at 3, 2, 3, 2, it's at 612, right? Which points like what? That's kind of like this, right? So we either want to go this direction or that direction. Have you guys ever thought about this? How do you, if I give you here short class on how to find perpendicular vectors in two dimensions. I give you the vector 1, 7. Perpendicular vector, minus 7, 1, or 7 minus 1. What you do? Flip the components and put a minus on one of them. Those give you perpendicular vectors, right? So if I want to find the vector which is perpendicular to 6, 12, what I would do is I would do like 12 minus 6, for example. But that won't work because that's not a unit vector. So what do I need to do? I need to normalize that, right? So I can divide that by the square root of 144, well, 180, right? But that could be simplified, right? Like a better way to do that. If we do 12 minus 6, that's equal to what? That's 2 times what? It's rather 6 times what? 2 minus 1. So my u hat that I want, it's 1 over the square root of 5, 2 minus 1. In fact, plus or minus this give 0 change at 3, 2. So I hope this discussion starts to give you some ideas, right? If I ask you a question about the rate of change of a function, you study its gradient. The magnitude gives you the maximum rate of change, and then you can pick different u hat to accomplish different rates of change within reason, right? The only rates of change available to you at the 0.32 for this function are those between minus root 180 and plus root 180. You can't change faster or slower than those two extremes. That's the lesson here. All right, well, I hope that should help you get started on a bunch of homework problems, actually. So